very impressively with nice picture, which is very good. Okay, now today will be okay. So I feel I'm missing 45 minutes. At the beginning I thought that 12 hours is a lot, but now I feel like so. But still, I want to reserve the last talk for this new, more modern stuff. So I'll try to be do it in a compact way. To the last thing I want to say about this homotopy, right? So first, we show how we can deal with the thin component which comes from cast or from unipotents, and at least we know that in the fixed in decomposition we either have cast or we have a commutative, in fact cyclic, but at the moment let's suppose commutative a group, Margulis group, a group of small elements. So we need something to deal with commuting transformation. So you see, we want to say something. So we know that the thin part in universal carbon is a union of nice convex sets with smooth boundary. But we want to say something about what's happened when they meet the corners. And okay, so this is the dilemma that. So actually, it's okay. So let's write it. So let alpha and beta be commuting isometry. So alpha beta is beta alpha. And A and B be positive number such that D alpha less than A is non-empty and D beta less than B is non-empty. So the sublevel sets are some convex nice sets, but both for the non-empty, and we already know, I showed it, that if they're non-empty, they must intersect. If they correspond to a commuting element, because when this set is beta invariant, because they commute. So if you take any element and look at the displacement there, you can project it to these convex sets, and then the projection the displacement just decreases. So they must intersect. But then we want to estimate the angle. I claim that, so we have this picture. This is B alpha less than A. And we have another set, convex set B beta less than T. And I claim that the angle here is at least pi over 2. It's at least time the angle that they need. So how do I formulate it? I take a normal. So this will be n beta. Let's say, and this will be at the same point, x. This will be n alpha. And to say that, so the angle between hyperplane, if you want, is pi minus the angle between the normal. So the claim will be let x be in the intersection of the boundary of d alpha less than A with d beta less than D, and alpha and beta in the tangent space the corresponding normal vector. Then the lemma, and then n alpha and n beta is non-negative. So the angle cannot be too small. Negative means that if the picture is like this. So then you see that this normal is pointing here and this normal is pointing here, then the product will be negative. So this is not the case. And so, okay, this lemma, this was lemma, I tried to prove it for 6 weeks. Like every day I was going to the sea and going back and forth on the shore, and unless there was wind, I went to surf. But every day, and then after 6 weeks, I suddenly realized that it's true, and I'll show you it's not a difficult argument. So here's the proof. So let C be a geodesic, with C of 0 equals x, and C dot of 0 is n alpha. So C is the following geodesic. We have C alpha less than A, and C. Okay, we have beta, and this is X, and C is the following geodesic. I don't want to draw beta yet. Now, okay. So now note that the set D alpha less than A is beta invariant. This set is beta invariant. This is because alpha and beta commute. The function, the displacement function, the alpha is beta invariant, and that's what the sublevel set is beta invariant. So do you see that, or should I write it down? Okay, this is a set. So this set is beta invariant. So you see, so this, if you want, you can draw your, but yeah, so this is orthogonal actually. Okay. Okay. So look at beta times C of t. So beta times C of t, it's another geodesic which has similar property. So let's draw this by x. So there will be a point here which is beta of x, beta times x, and this will be another geodesic, beta times c. And you see that both of them are orthogonal to these convex sets. So you see, you can actually prove, but at least it's easy to see, and then when you think of it, it's not so hard to prove, that the convexity, and when I say convexity, I mean both convexity of these sets and one convexity of the metric, the non-positive curvature. Okay, but again, convexity of the set is the corollary of convexity of the metric. So convexity implies that the function t goes to the distance between c of t and beta of c of t is non-decreasing for t greater or equal to. This function, the distance is the same. Actually, it's the same as saying that projection to the nearest point is decreasing distance. This at least will say that if the value here is bigger than the value here. But then convexity also will imply that it's non-decreasing everywhere. Okay. But this implies that the d to the t, where t equals 0, of course, the derivative is defined, we're taking limits when t goes to 0 positive, because the function is just defined for positive number, but this is well defined. Of this function, this is non-negative. But what is it? this is the same as, let me write it like this, of the distance function d beta of c of t. And this is the same as the gradient of this function x of 0, which times c dot of 0. Now, what is this? Gradient of d beta, you know, so now recall that okay, this is x. C of 0 is x. And gradient d beta is, this is in, let's write it this way, this is n beta. It's not equal, but it's the same direction up to normalization. So this is, the gradient of d beta is orthogonal to the sublevel sets, and n beta is the normal of the sublevel sets. And this is n alpha. So this implies that n alpha times n beta. Okay, this is this lemma. Okay, so it's very simple, but I was seeing a lot of this, and actually I was very happy because in 2005 I met Dan Moscow, and he told me that he looked at my paper and he said he was very impressed by lemma 7.1. And this is lemma 7.1. So he exactly knew what he said. So, yeah.
And this actually holds negative curvature.
Yes, this works in cut zero spaces. Yeah, in very general situation. And actually, I think there should be application for this because sublevel sets or even fixed point, you know that the set of fixed point must be the same. This idea can be generalized in many situations. So I don't know any application of it for other use, but yeah. Okay, then there is another lemma, the second lemma, which is, okay, I will call it monotonicity of angle. No, of angle. So you know, just recall. We now know the sublevel sets, and we know that the sublevel sets have good angle between them, so we control the angle. But then we take neighborhoods. But I think it's very intuitively that when you take neighborhoods, the angle can only grow. It's when you feel it when you take very large neighborhood, the angle will be almost high. So this is at least intuitively it's true. So let's formulate it the following way. So angle only grows. So let A and B be convex sets with smooth boundary. Between boundary and define for positive t, define h of t be the infimum, could be a negative number, of n x n, that's right, xa and x and xa dot nx well, these are the normal. So nxa t and nxbt. So and okay, I don't want to spend time writing it, but this is x, and I take the normal here, and the infimum is over all x in the intersection. So this is if you want the minimal. You look at the point where the angle is minimal. Oh, sorry, when the angle is minimal, the inner product maximum. So it should be the sum. So we want the angle to be small, so we want this product to be large. I mean, okay, this product is something between 1 and -1, but we want it to be positive. And the lemma says,
in your notation, A and B are the inside sets, right?
sorry?
What is A and B?
This is A,
And that is B.
this is B,
So
this is A,
yeah, yes, oh, that's how you write.
this is B,
Okay.
T, and I take X over, I look at the whole intersection and let X be any point in the intersection, and this will be n x of bt, and this will be n x of a. And then I claim that ht is something non-increasing or non-increasing. Then h of t is non-increasing. So, or non-decreasing.
Non-decreasing, I think, right? Because you will take pi minus that.
Yes. So, yeah, non-decreasing. So, okay. I want the angle to grow. Yeah, it's so this is actually. No,
Settings.
I think it's okay. So, yeah, you see, yeah. At the end, you see the left direction. At the end, this angle will become pi. And then this will be -1. Then it will be 0. Actually, this number is between 0.
Non-decreasing. I think it's non-decreasing.
Non-decreasing? Okay, I will trust you. Non-decreasing, yeah. Okay, I'm confused, but I trust you. So HT is non-decreasing. And that's the lemma. And proof, intuitively, it's clear. When you try to write a proof, it's not so easy, it's technical, and let me just write the proof. Proof that I wrote relies on the Lagrange multiplier theorem. So when you try to write a formal proof, then you have to prove something. So, okay, so it relies on the Lagrange multiplier theorem, but maybe if you start to try to prove it, you will get another proof. But anyhow, it's very intuitive. So let's leave it like this with pictures, and you can refer to the proof. Okay, so this is good. So we know that even when we take this, so still, when proving this lemma about constructing a simplicial complex, we needed some, in any point we needed a good direction. But now it's quite clear that there is a good direction, because all these inner products are good, and take something in the middle. So this will be the next lemma. Next lemma, which I will call existence good direction. So this is lemma about vectors in Euclidean space. So given D, there is B, D is the dimension, oh, D is not good at dimension, which, how should I denote it? N.
Yeah.
Given N, there is B of N, such that for any set of vectors, of unit vectors, let's call them Ni, some set, and this is in the sphere of, in Rn, in the unit sphere. There is a vector, there is some vector n, which is not necessarily in the set, but there exists some vector n, such that n in a product with ni is at least 1 over b for any I. This is intuitively very clear, but again, there is something to prove, because when you intuitively think of it, so if you have a collection of vector with a positive inner product, oh, sorry. Such that Ni product Nj is non-negative for any Ij in I, then there exists n hat such that, yeah, it's not, of course, you can take all the vectors in the sphere and then it's not. And when you think about it, it's very clear, because this condition tells you, at least in the plane, that they're all in the 1/4 of the plane. But this realization is not true in dimension 5 or more. If you have a set of a vector which satisfies this, it's not true that you can put it in the positive part of Rn. For large n, it's not true. So we have to prove something, but it's not so hard. So here's the proof. So there exists B such that the maximal, okay, I tell you what it is. Let B be the, if you want, the one entropy of the sphere. So what does it mean? The size, the maximal size of one discrete set in S n minus 1. So this is a compact set, and there is some B. Okay. So given a set Ni as in the lemma, let F inside this set,
The maximum size means the cardinality, right?
be the maximal size of one discrete set.
Size means cardinality.
Yeah, maximal cardinality. And now look at the, okay. So now let's be a maximal one discrete set in Ni. One set. Then you know that the size of it is at most, actually I want to call this number 2b. Let b be the, let's 2b. I call it 2b. So this is at most 2b. And I will tell you what is n. Define n to be the sum of ni side f, and then you have to normalize. So this is n. Just the norm, the average of them of this maximal set, this maximal set. Okay. Okay. Now for every j in for every j in my set, and every ni in f, ni and j is non-negative. That's the possibility. But for one of them, one ni in f, the distance to nj is at most 1, because otherwise this f was not maximal. So if the distance is at most 1, the inner product is at least 1/2. We have that ni times nj is at least 1/2. And now if you compute, this implies that nj product n, which is the average of them, will be at least 1/2 divided by 2b. Oh, what should be 1/2? Then, if you divide, so you get here, so this, if you multiply n by nj, this will give you at least 1/2, and then you divide by 1/2 t, then this will be at least. That's the proof of the lemma. And this lemma tells you what is the good direction. Now I can formulate a theorem which follow from our lemma 4.1. Lemma 4.1 was the lemma that, the technical lemma that we worked quite hard to prove, that told us how to construct a simplicial complex in a fixed submanifold boundary. And now I will formulate a theorem which is less general, but more practical. And the theorem is as follows. Theorem. And let's call it by name. Unit content as well as abelian alpha. This will be the name of the theorem. And what does it mean? So let epsilon be bigger than 0. So it's not necessarily the Margulis constant, but it's something related. The Margulis constant over some constant, so it's smaller than Margulis constant. And suppose that M prime is inside the thick part, is a submanifold connected submanifold with boundary. complement, the same part, no? And x tilde, okay, x tilde is given by union gamma in some gamma prime. Gamma prime is not a group, it's a subset, which is, let's write a conjugate, some conjugating variant subset, some subset, variant under conjugation, gamma. And so this is given by the gamma less than constant, so less than epsilon prime. So epsilon prime, let epsilon, the two constants. So epsilon bigger than epsilon prime bigger than 0. Epsilon will be, you can take 1/2 or 1/3 of modulus lemma, and epsilon prime will be something smaller by some constant. And this is because if I would take all the elements in gamma, set identity, then it would be, I will take epsilon equal epsilon prime. But if I take, you saw sometimes we take only unipotent, sometimes we want to take, we don't want to use all of them because then it's hard to control this set. So I take only some of them. And assume and suppose, so this is if you want okay, given x, for any x, let define, for any x in S, let I call it gamma x, but let's call it gamma x prime. So this will be a group. This is the group generated by all the elements in gamma prime, such that the gamma of x is less than epsilon prime. So the group of small elements. And assume that for every x, this group is either unipotent or abelian. Either it's an abelian group or it's a unipotent group. Unipotent, I mean containing a connected unipotent. Then M prime is homotopic to a d alpha volume M prime simplicial complex. And d and alpha depends on S, epsilon, and epsilon prime. But when we use it, epsilon and epsilon prime will be determined by S, so d and alpha depend on S. And why this theorem is, why, okay, I will not try to prove it, but it's easy for any of you who follow the lecture to complete the proof of it, because, okay, we spent the lecture to explain what happened, last lecture was explained to tell what happened in the unipotent case, and today I told you what to do in the commutative case. I told you that if everything commute, then all the angles are good, and then I can find a good direction at this B, so everything is on the board, and you can apply proof. Let me just write one lemma for one line for the proof, but this immediate application of proof. In the last lecture, we saw, how do you spell so? S-E-A or?
S-A.
S?
We show.
So.
S-A-W.
We saw how to treat It's the unipotent case. And today, we saw how we can apply lemma for one for the abelian case, commutative case. So if you recall, lemma for one required us a direction and a constant, and they are on the board. Okay, so we are fine. So with this theorem, I can now repeat to the, let's say, first the rank one case. So now we can, I will do the rank one case, and then I will do shortly the high rank non-compact, because we have all the we have everything, and to verify all the details, it's like playing with epsilon, delta, and but we have everything, and everyone should see that it's okay. First the rank one. So actually, there are two ways to continue that. One is, what is the rank one case? We know that our manifold is something like that. We want every cusp can be deformed to its boundary. Every tube is a tubular neighborhood of a short geodesic. So if the dimension is at least 4, when you throw a geodesic, you don't change the homotopy type. So we will throw the geodesic, then we have to prove that we can contract to the thick part, and then we apply this lemma, because now you see, we have this situation. Every gamma x epsilon prime, every gamma x epsilon prime will be either abelian or unipotent. So we can apply this lemma. So actually, so let me just write. In the rank one case, the thick so in the rank one case, let gamma prime be everything, gamma minus identity. So we can let n tilde be the union of all axes of hyperbolic element with displacement at most epsilon. Okay, and sorry, epsilon is in this case epsilon tag, which is Margulis constant. Let's say divided by 10. I think if you divide by 2, it's enough, but just for sure. So this is a sub. So the dimension of n is 1. It's not connected, but it's one-dimensional. And it's gamma invariant, and blah blah blah. And you can project it to a manifold. So we see that pi 1 of m is the same as pi 1 of m minus n. If the dimension of S is at least 4. And here you see that's why I need the dimension at least 4. If you throw out from a 4-dimensional manifold a 1-dimensional line, a geodesic, you don't change its fundamental group. Every 2 loops, which are homotopy between loops is something 2-dimensional. if it crosses the bad part and the one-dimensional bad part, you can push it. There's still one dimension to push it because you have 4 dimensions. 1 dimension is taken by n, 2 dimensions are taken by the homotopy, but you can still push it. So this is classical basic lemma in homotopy theory. When you draw something of codimension 3 or more, then it doesn't change the fundamental. So this is good. Okay. So now, and we define m prime as before. So m prime b or m prime tilde b intersection over all gamma in gamma minus identity of b gamma greater or equal to epsilon. So this is actually the epsilon thick part. Epsilon thick part. Or m, the quotient of it, m prime, which is m prime tilde minus gamma, as always, is the epsilon thick part. And first, you have to show that m minus n is homotopic to m prime. So how to show it? So you can use our, we had a very, we had a very general way to do deformation retract that increase function, but in this case you can just use by the star contraction. By the star contraction. By the star contraction. So, okay, what do I mean by that again? So, what do I mean by that? So we call what was the star contraction? So we know how the thin part looks like. So either is a cusp, and cusp you can contract just, there is a unique fixed point at infinity, and you can do the star contraction coming from this point. And in the tube case, we just know that there is a geodesic, and it's a neighborhood of this geodesic. So this neighborhood may be complicated, yes, but still, it's a star neighborhood. It's a star shape. The thin part, or each thin component, let's say, each thin component is, say, nicely star-shaped, is respect to a short geodesic or a point at 15. Okay, and then by the last theorems, by theorem, let's call it by a name. So, okay, let's for now just call it star. By theorem star, m prime is homotopic to G alpha volume M in visual properties. Okay, in the theorem it's written volume M prime, but volume M is at least volume M prime, so it's okay. And that's it. We're done with the round one. Okay. I have 10 more minutes for the round one case. So I want to say that there is another way. There is another way to do it in the round one. Not really another way to do it, but just another way to explain this line. Or the line that fundamental loop is the same as fundamental loop, the thick part, and using Van Kampen theorem. Since you really understand the thin part, you know how to compute Van Kampen using Van Kampen, and you can see that it doesn't change. I don't have time to do that. I just want to say what goes wrong in dimension 3. In dimension 3, you do change the fundamental group when you draw the geodesics. So in dimension 3, so what's the situation in dimension 8? In dimension 3, when we draw a geodesic, we change the fundamental group. But how many short geodesics there are? It's bounded by the volume. So we know how we change the fundamental group. When we remove a geodesic, we do change the fundamental. But we know how we change. If we glue it back, we don't need to add generators. We just need to add one relation. What is the relation? Is that something that goes around this geodesic and previously cannot be contracted, now can be contracted. So we just need to add one relation. When we glue it back again, if we glue it back again, we need to add one relation. Okay, and this relation can actually be quite long. We have no control on how long is this relation. But this relation involves only, you can do it that it involves only two generators, but it could be quite long relation. So I don't want to elaborate too much because of lack of time. But since the number of short geodesic, of closed geodesic, of length of closed geodesic, of length at most epsilon is bounded by the number, is at most the number of thin components, which is at most a constant times the volume of M, we get that the fundamental group of M is the fundamental group of M prime divided by a normal subgroup generated by so this will be a normal subgroup generated by geodesic. So let's show geodesic. Let's call it. Let's denote like this. So if you want, it's there is a generator in relation such that number of generators, the number of relation is most constant times volume. Okay, I did it a bit fast, but I think it's understood. So you can actually try to understand more what is the kind of the relation that you don't control the LED and blah blah blah. But I don't want to say more about this because I have 5 more minutes about the rank 1. Oh, now it's 10 to 12.
It's
5 to 12.
5 minutes to 12 for in my watch.
Okay, 5 to 12. Okay, so I have 5 more minutes about the rank 1 because then I want to describe the higher rank. Okay, so in the rank 1, the story is that first, it was a joint paper with the, okay, so this all the work started joint paper, so theorem, before my paper, before the Duke paper, so 2 years before, together with the other Max Burger, Shachar Moses and Alex Lubowski, we proved the following theorem. We proved that for hyperbolic manifolds, so one of the corollaries of this theorem is the number, using most rigidity, is that the number of S manifold of volume at most V is at most V to the C. We proved that given N, which is at least 4, there are A constant A and B, such that for any V which is at least some number, the number of hyperbolic N manifold of volume at most V is bounded by V to the AV to the VV from above and by EV to the AV from below. So the number of hyperbolic manifold behaves like this. In the paper we wanted to be nicer, so we took log. If you take log on both sides, and this becomes a multiplicative constant, so it's not nicer, but this is what we proved. So, so by the way, the story was like this. So I started my PhD with Shachar, and he suggested me, after 1 year, he suggested me to estimate, so there is this one finiteness theorem, and he suggested me to give a concrete bound for one finiteness theorem, and he suggested me to follow Prasad work. So Gopal Prasad has a fantastic paper that gives you a volume formula for arithmetic manifolds. Very, very brilliant paper in the journal of IGS, and he suggested me to do that, to try to use his idea to get a concrete bound. And then he told me, you know, we tried a geometric approach a few years ago with Burger and Lubowski, and we tried to prove this, but there was a gap. And then I looked at the paper, and after a few months I managed to correct the gap, and this was this. And then I was so fascinated about this geometric approach, I continued and tried to do the homotopy in general. So this was the beginning of this work. And so
There's one question.
Yeah.
I have one question.
Yeah, sure.
Yeah, maybe that's silly. So what happened in dimension 2 in?
Oh, in dimension 2, I ignored it. You weren't here last week, but I said that in dimension 2, all the results concerning the homotopy type are easy. You can deduce it from Gauss-Bonnet theorem, because Gauss-Bonnet theorem tell you that if you know the volume, you actually know the topology of the manifold. You know the genus, the order characteristic, and then you can construct any relation. So I can ignore dimension 2. Of course, you cannot bound the number of manifolds because there are continuously many the type Miller theory. So let me explain the lower bound in this work. So the lower bound, I will spend 5 minutes on the lower bound. Actually, the lower bound in this theorem was strangely used by physicists. There are some papers of physicists who are trying to estimate the cosmological constant. So it sounds very fascinating, and they use the lower bound that we gave. So in two cases. Yeah. So the lower bound. So let me explain the lower bound. And so the lower bound that I will explain is, as in the original paper, it will be given by non-arithmetic manifolds. But later, in a later work, we also give lower bound for arithmetic manifold. In fact, for arithmetic manifold, we know the precise growth in okay, no, not in dimension 2, not in dimension, yeah, only in dimension 2. But okay, later we gave also a low bound in arithmetic manifold, but in this paper, non-arithmetic. So
in this paper, non-arithmetic.
Non-arithmetic.
Oh, I see.
So there exists a manifold, let's say a non-arithmetic manifold, compact as well as non-compact. So you can take it to be compact, non-compact, non-arithmetic, arithmetic. The low bound show that there are many of all this type. M such that gamma, the fundamental group of M, has a free quotient, has an F2 quotient. So this is well known. So this is you can
Barnum Gromov, Barnum
Yeah.
Everline paper, I think.
no, there is the Gromov Petetsky Shapiro paper. So
Gromov.
yeah, Gromov Petetsky Shapiro showed us, gave a very beautiful way to construct a non-arithmetic manifold. In fact, it's the only way to construct infinite family of non-arithmetic hyperbolic manifold. But the way they do it is they start with two arithmetic manifold given by quadratic form construction, standard construction of arithmetic manifold, and they show that each of them, they admit that they are non-isomorphic, but they admit isomorphic submanifold of codimension 1. And then they take two such manifold, which admit, and they glue them. Okay, it's not like this. It's in higher dimension, but the idea is that they glue two arithmetic ones. And they glue two arithmetics and they show that it's non-arithmetic. And the way they show that it's non-arithmetic, they show that the commensurator is discrete. And Margulis' criterion tell you that. So okay, this is by Ballman, by Gromov and Petetsky Shapiro. Let me write just PS paper. So this is a classical paper, again in Journal of IGS. But there are other ways to do it. In fact, there are other ways to prove just the existence of such, and you can also prove the existence of arithmetic such manifold. So, no, actually, to prove non-arithmetic such case, it's only by Gromov, but you can also show the arithmetic. Okay, so let gamma be such a group. So we know that the commensurator in G of gamma, where G is the SON1, contains gamma as a subgroup of finite index. So this is again a lattice, maximal lattice. Okay. So we know the number of subgroup of F2 of index n is something like n factorial, right? You can estimate it's behave like n to the n. So the number of index n subgroups. So this is known exactly, and it's not so hard to compute it. So it's the same as saying, so what is the subgroup of index m? It means that every subgroup of index n, it gives you a map from F2 to the symmetric group on n, and you just count how many such map you have. So you have two generators, and you have each of them, you set it to one of the generator of Sn, so it's n factorial, and so it's, okay, so the number of subgroups, let me just write, this behave like n to some point. Okay, all of them are isomorphic. All the same. It's a free group on the number generated. But when you pull them back to gamma, I claim they are non-isomorphic. Most of them are non-isomorphic. Why? Because if two of them are isomorphic, then they're conjugate. If they're conjugate, the element that conjugates them is inside this group. But this group is almost gamma. So also if you count them, so there is some counting argument you have to show, but although all of them are isomorphic, all of these are isomorphic, the pullbacks pull back to gamma are non-isomorphic. Maybe some of them do, but are almost all disjoint. Almost all. Okay, each of them could be isomorphic to finitely many, boundedly many. Almost all. Let me write almost all non-conjugate by this. So this is by the way Margulis criterion for arithmeticity. Right? Margulis criterion says that exactly if gamma is arithmetic lattice, then the commensurator is dense. If gamma is non-arithmetic, the commensurator is discrete. It's like lattice itself. That's Margulis criterion. So and by this, I'm not telling all the details, but it's easy to figure out, or you can look at the paper. It's half-page proof. By this, hence, by monster rigidity, if they are not rigidity, lattices which are not conjugate are not isomorphic. Not isomorphic. That's it. You get fundamental group are non-isomorphic, and you get plenty of length. That's the way. Okay. So that's explained. Okay, now I've finished all I want to say about the rank point case. Again, if you understand the lower bound in more detail, look at our paper. It's half-page explanation. You will see it here. A bit more details. What about the higher rank? I have in half an hour to tell you how to complete the proof in the higher rank case. So this is, in a sense, the most difficult case, but we have all the tools, everything. And I'm not going to do it epsilon delta this. I just tell you the idea.
So this is true for all rank 1 spaces, is it, or just hyperbolic?
This is just hyperbolic.
Lower bound is
Yeah, we don't know in either case.
but the upper bound is true for all rank 1.
Upper bound is true
for all the symmetric
every
spaces.
symmetric space. Yes. Lower bound is just for and okay. The remaining, if you want also the main, the remaining higher rank. So we assume that rank S is at least 2. So in that case, by Margulis arithmeticity theorem, every finite volume manifold is arithmetic. Every S manifold of finite volume is arithmetic. So So by the way, when we say arithmeticity theorem, we always assume rank 1, a higher rank, but it's also true in some rank 1 cases, in SPN1 and F4 minus 20. So not by Margulis, but by Corlett and Gomo Shen. So it's also true in the rank 1 case, but rank 1 we know how to do geometry. All of them are arithmetic. Since we proved a stronger theorem, statement for non-uniform one, for non-compact arithmetic manifold, we may assume that we now have to take care only of the complex cases. We may now consider only complex. Okay, that's a good thing. So, okay. This is in a sense why I did a rank 1 separately. So, okay, of course it's better to do the rank 1 separately because in rank 1 you exactly see what's happened, but in contrary to the higher rank. But also now you can simplify. Okay. So we tried to do the same, like similar to what we did in the third lecture. Third lecture, we started with it was an orbifold actually, and we threw out the singular submanifold. We also did it in the rank 1, we threw out the geodesic, but we want to show minimal sets of hyperbolic element with small displacement. The problem is that we don't have the nice 16 decomposition. We don't have a nice 16 decomposition. We don't have that. Actually, I wanted, if I had a bit more time, I would describe some conjecture in number theory that says that we have a very nice 16 decomposition, we don't have a thing. So there is a famous conjecture in number theory that says that in arithmetic case, you don't have a thin part. So maybe, if I had, okay, maybe you will allow me a few minutes and I will describe. But these are conjecture, we don't know them, and the thin part, it's quite complicated. So actually, before I published this paper, before I knew how to do, before I had this idea to throw out singular manifold and do this Morse theory, that's basic Morse theory, I thought to use Van Kampen also in the higher rank case, and then I managed to do it if you assume that your manifold is regular in the sense that all the isometries are have axis in regular direction. And then you can prove some 16 decomposition. So the thin part will not be tubular neighborhood of a geodesic, but will be a tubular neighborhood of a torus, and then it's that. But in the higher rank case, what's happened is that the thin part can intersect. You can have a thin part, and this will be not 1 dimension, but 2 or 3 dimension. And this could be also the thin part of something else. And then what you can have that maybe this has larger thin part, and it's hard to describe it, but I don't know how to. So you can have a flat that is the axis of some geodesic, but the flat is in a singular direction, and then there is another flat which intersects it orthogonally, and this corresponds to other singular direction. So you don't know how to do it, and maybe all the thing components are connected somehow, and you cannot control it's hard to control the topology. So this is why I said at some point I have this idea that, okay, let's throw all of them, and then you have to use, so I already proved in the third lecture when I described the number of generators of lattices, I proved the following lemma: if G is hyperbolic, I prove that the codimension inside S of min G is the set of x's of G, the union of the set of x's, is at most, is at least the dimension of G mod P, where P is a parabolic subgroup corresponding to the point of infinity that the axis, the end of the axis. So I proved it. So, okay. And then we have this other lemma or proposition that it's funny because I needed this, and exactly at the same time my friend Uri Bader was working on his PhD, and he with Amos Nevo, and they proved for different reasons, they proved the following: for any semi-simple Lie group, the dimension, so they prove something stronger, but the dimension of G mod P, when P is parabolic, so dimension of G mod P is at least the dimension of the rank. Okay, for any simple, the dimension is at least the rank. And moreover, equality can happen. Equality implies that G is locally isomorphic to SLN. In SLN, you have a parabolic subgroup for dimension n-1, which is the rank, but that's the only case.
Is this true for all parabolic or just
for every parabolic? They computed, they have to give more information in the paper. So I refer to the paper in my paper, and they needed more precise information about codimension of algebraic subgroup. But in particular,
rank is the real rank.
Rank is the real rank. Yeah. For me, yeah, in all the lecture when I denote rank, I mean the real rank. Yeah, and also it's the dimension of the real quotient. So, so in particular, we need if you remember, we need that if the codimension is 3 or more, we are fine. So if the rank is 3 or more, we are fine. The only problem is rank 2. But again, the only problem is rank 2 and SLN, because equality can always follow SLN. So our only problem arises, so this is why this explains the only problem for our needs this is sufficient as long as, or except the cases, except in the cases where G is SL3 or SL2 cross SL. These are the cases where
The actual cases.
these are the other group of rank 2 like SO and 2, but this case, in that case the codimension is at least 3 because the equality can only for SL. But so these are the only two cases that this proposition of Bader and Levaux, and I should write the name. So this is the only cases that I cannot apply. And okay, I can apply, but it's not sufficient for me because then I throw out something of dimension 2. Okay. What we do now? I will write it fast. It's actually quite similar. The argument now is similar to things that we saw. Similar to things that we saw. So what do I mean? In the third lecture, given G hyperbolic, we define a thing, I call it G bar, to be G to the power M to the power I, where I was less than some constant nu, and we had nu is M to the nu, such that if you want, the centralizer in G of G bar is the same as the centralizer in G of G bar to the power M. And M is the constant. M is the constant for Margulis level. Okay, we could replace every element by some power. And okay, this is one thing I have to remark. Another thing, okay. Second thing is, okay, so now I define let epsilon prime, if you want, be epsilon over mu. Again, epsilon is, let's say, epsilon of Margulis divided by 3. That's Ribot. And define n tilde will be the union of mean gamma bar such that gamma is in gamma minus 1. I don't need to say that it's hyperbolic because I already said that gamma is a uniform lattice, quotient free, that everything is hyperbolic there. And I also want that the infimum of the displacement of gamma bar is less than epsilon prime. So this is, and we know that if we are not in these cases, under the assumption which that S is not H2 cross H2 and not SO3 mod SO3. Under these two assumptions, we know that the codimension of N is at least 3. We're fine. Now, now we can apply everything. So note that so why I need is going to power m, because now remember that we had a strong version of Margulis lemma only in the non-uniform case. So now I don't have the strong version of Margulis lemma, but gamma x epsilon prime, which is defined as a group generated by all, say, gamma bar, such that gamma is in gamma minus identity, and d gamma bar, or the infimum of this, is less than epsilon prime. So this group contains an abelian subgroup of index at most n. So why it is abelian? Margulis lemma tells us that there is a subgroup of index n which is contained in a connected nilpotent. But connected nilpotent, which it means that you can conjugate it to the upper triangular inside G and C. But then you look at the commutator. When you look at commutator, you are left with unipotent. But in gamma, there are no unipotent, so you're left with nothing. So the commutator is trivial. Okay, so is it okay? I don't need to write it. So this is abelian. Abelian group, the thing is that commuting isometries, the mean set intersect. For commuting, so this is something I also said in the third lecture, isometries, really I could call it isometry, the mean set intersects. They have the mean set is a sublevel set. So at any point, now to prove the theorem, remember all we need to do is at any point to define a direction which increases displacement and a good direction. And so at any point we can find a direction. This helps in defining the direction and x. Why? Because you have a mean set. Suppose you are at some point x, and you want to know where okay, the direction doesn't tell you where to flow. It just tell you that you satisfy some condition, and then this direction will change non-continuously, not measurably. But using the existing sign direction, we had a continuous way to define the formation of the fact. But here, suppose this is mean of gamma 1, and it intersects mean of gamma 2. Maybe they intersect on, so this is a flat, and this is a flat, and they intersect along a line. So this is the intersection. And you have some point x, which is not, x is not in this, and is not in this. It's not in this plane, but you can project it, projection of x to the intersection. So mean gamma 1, section mean gamma 2. You can project it. And this direction will tell you what is direction which take you further from the intersection. This will be the direction. This defines the direction x. At any point which is not in the bed singular submanifold that we draw, you can define a direction. If you're close enough to it, you can define a direction. And then you have to say, but you have to know that direction x, in the direction n of x, all the displacement function, the directional derivative increased by some amount. So each of them increased by something because you get farther from the mean cell. But why you can bound it from below? So to define beta, one uses compactness. Because you have only compactly many points. You need to. What is beta? Beta, I told you, if the displacement is t, then I need the inner product, the directional derivative of any displacement function to be at least beta of t. So I look at all elements and all points in my manifold where the inductivity radius is exactly t over 2. Exactly, the displacement is exactly t. In each of them, there is a best direction, and it changes continuously. The best direction changes continuously, and in each direction there is some amount which changes continuously. I take its minimum of a low compact set, and this defines it. And now I think, at least intuitively, so I hope everything is written. One can complete it. Okay, we're done with the theorem, and now the question is whether I should stop here, because the next lecture will be about a bit different work. Or if you want me to say 10 minutes about this arithmetic lemma projection.
Yeah.
What do you think?
Yeah, please. Yeah, go ahead.
Yeah. Okay.
I just want to make 2 remarks.
Yeah, sure.
One, I think when you wrote that normal thing, when you take neighborhoods, I think you were right about non-increasing. We said non-decreasing.
I was right?
You were right. Yeah.
Okay.
Suppose you take 2 circles which are intersecting and then you take neighborhoods, the normal direction actually keeps increasing.
Yeah. No, yes.
Yeah, that's okay. And second question I want to ask is, so in the lower bound, when you mentioned you proof of non-arithmetic cases,
Yeah.
and in the hyperbolic case, you use the Gromov-Shapiro construction.
Yeah.
But did you also say that for arithmetic also some?
Yeah, there is a later paper joint of me and Bolalepetsky and Lubotkin and Shalev.
Okay.
When we study in a completely different tools, we study growth of the number of arithmetic manifold in dimension 2 or 3. And there we prove the lower bound by using arithmetic, but the lower bound is in any dimension. It's also in either dimension.
And it's only again for only hyperbolic, real hyperbolic.
Always only 5.
Yeah.
Only 5. Yes. And okay, so actually, so there are 2 things. So one, I wanted to describe. At least it's good. It's so maybe I will not describe in detail, but one thing that when I prove the arithmetic Margulis lemma for non-uniform case, maybe it's in the lecture note. It's good to write there that it follows from the arithmetic variant of Margulis lemma, version of Margulis lemma for non-uniform lattices, manifold, that there exists some positive number, delta bigger than 0, such that in delta depend on S, such that in arithmetic, if you do the same thing, the composition of the plus delta, actually it was epsilon, okay. If you do the 16 composition with delta, there are no thin components which are compact, only casts. So in particular, every arithmetic S manifold, arithmetic non-compact, non-uniform S manifold, M admits no geodesic closed geodesic of length less than delta. So,
Sorry, can you quickly remind us how this follows?
the Margulis lemma tell you that if you have a group generated by small element, then everything there must be unipotent.
That's
Yeah. And unipotent, so you know, if you have a unipotent, so by the way, if you have a unipotent, you have, in the cast, you have arbitrarily short loops, right? But this will not be geodesic. You can go in a geodesic, but you start and end not in some angle, so it's not a closed geodesic.
Loop.
So this is not a geodesic. Not a closed geodesic. So you have short loops, arbitrarily short loops, but not geodesic. Geodesic you don't know. So maybe you can add that to that argument, to the discussion, and then you can, when I give a course about arithmetic groups, I like to, the first example of non-arithmetic manifold, I draw this of a non-arithmetic surface. So what you do, you just take something which is non-compact, and you do it thin enough, and say it cannot be arithmetic if it's thin enough. Okay, maybe this is arithmetic. This cannot be arithmetic. So if it's sufficient, you can actually compute what is the minimum or what some minimum. Yeah. So this is nice to see. But then there is a conjecture of Margulis. So I will not write it. You can look in section 10 in my paper, and it's good to be remarked in the lecture notes, but there is a conjecture of Margulis that the same holds for compact manifolds. For compact manifold, if they are arithmetic, there should be a lower bound of the shortest geodesic. This is a difficult conjecture. In fact, there is a paper by Suri.
Arithmetic, right?
Arithmetic, of course, only for arithmetic. And there is a paper by Suri that shows that in dimension 2, if you consider only surfaces, that's like Riemann surfaces, then this is equivalent to the fact that there is a gap between 1 and the lowest Salem number. So what is a Salem number? A Salem number is an algebraic number such that all its